I'm Grant Gothing. I am an ATE product manager at Bloomy Controls. I'm a certified LabVIEW and test stand architect and a certified professional instructor. And I've been with Bloomy for just almost 10 years now, mainly focusing on ATE for various customers. We're a systems integrator. And so we do a lot of test systems for a wide range of industries, from medical devices to consumer products, aerospace, electric vehicles, huge range of products. And so what I'm presenting on today within the hardware abstraction layers and measurement abstraction layers is kind of some knowledge that we've gained over the last, at least I've gained over the last 10 years of working through a lot of different customers and seeing a lot of the common challenges. So when developing automated test equipment, especially on the hardware side, I think a lot of us are in a similar boat probably. We use modular equipment, PXI equipment, mass interconnects in order to improve the scalability and flexibility of our test systems. But in order to have a really flexible, scalable test system, your software really needs to be as modular as your hardware. And so we use abstraction layers in order to allow the test system software to adapt just as easily as your hardware can adapt. And so something as simple as swapping out a power supply because maybe you had equipment failure, you had to pull something off the shelf, or you have an obsolete instrument, could take dozens to hundreds of hours to update all of your test procedures if you need to rewrite every single driver. And so what we're trying to talk about today is how to mitigate that risk and mitigate the exposure to long development times and rework times due to simple things like a power supply change or a switch matrix change. And this isn't something that's a far-fetched idea. Just recently in the last 2 months, I had to do a duplicate system for a customer where there was an obsolete power supply. The second system, we couldn't use the same power supply. And we were able to use, instead of an Amrel power supply, that was the first one, we used the Xantrex for the second one. And we were able to get them to run exact same code bases on both systems without having to change any of the test sequence files. So, as test engineers, we typically are plagued with a rushed development cycle. We're dealing with poorly defined requirements, and because of that, we kind of have this evolving test procedure. Oftentimes, the test procedures get to us by the time that they want the test system, or we may not even get aboard until the system is ready to go into production. And so we need to mitigate some of these issues by developing hardware and software in parallel. And so in order to do that, you really need multiple engineers working in parallel on these two separate areas. And so now once your system gets deployed, your problems don't really go away. You now have, if you have a long system life cycle, equipment obsolescence, you might have failing instruments or may have to send instruments out to be calibrated. And as products update and you have new requirements, you now have to modify, you may have to modify test sequences or instrumentation to map to handle those requirements changes. So hardware abstraction layer is from the instrument point of view. Measurement abstraction layer is from the unit under test point of view. So a really good example of this is printers or printer dialogues. When you go to print a device or print a file from Word, you don't really go in there and send these serial commands down over the lines to tell the printer how to configure itself and what data to send. Printer manufacturers define or follow some standards that for configuring and receiving the data that needs to be printed. And so with these standards, they define the methods and the parameters associated with what it takes to print a document. Now, you still don't necessarily write code to interface with these higher level parameters, and those high level parameters are essentially a measurement or a hardware abstraction layer. They abstract the hardware into some generic functions that you're going to perform. So you as a person printing, you're still not calling those individual hardware functions. You're opening up a dialogue, and that dialogue is more of the measurement abstraction layer. It's providing the pertinent information to you so that you can print, you can set the landscape or portrait or what paper size you're going to use. So the measurement abstraction layer really puts it into the developer's standpoint. So what are the benefits? Really, by using software, you're able to develop your fixturing and your instrumentation in parallel with your test sequence development. And by decoupling these, it really gives you an API that everyone has access to for developing, gives you a common way to interface with different instrumentation, with different measurement and signal types. And by doing this, you reduce your development time, and you're able to better handle changes to instruments and requirements. And as you get farther along, once you've deployed your system and it's out in the field and you have an obsolete instrument, it's much easier to swap out that obsolete instrument for, that Amaral power supply with a Xantrex power supply, because you've abstracted away that information. You've said, all I want to do is I want to set a voltage, and you use your hardware abstraction layer and your measurement abstraction layer to translate that to the instrument-specific commands. So to kind of understand this, let's take a step back and take a look at the anatomy of a typical piece of test system software. Typically, you have a test sequencer like TestStand, and it calls code modules. And these code modules could be LabVIEW VIs or CDLLs, ActiveX calls. But typically, they implement some sort of function that you're trying to perform with some instrumentation. So you might have a driver or a wrapper that does a switch to DMM, or a power supply with a ripple measurement. And so you write these code modules that do exactly what you're trying to do, and they interface with specific pieces of hardware. So as an example, let's take a switch to DMM, which is one of the most common things we would do in a piece of automated test equipment. So here's an example. On the right, you actually have almost exactly what is in the NIExample finder for a switch to DMM example. And so you define your switch resource and what the topology is. In this case, we're using a MUX, and so you have to define what channel you're using for that MUX. And then you do the same thing with your DMM. In TestStand, you call that VI. You have all those inputs and outputs. You pass those in, and from your step definitions, you can kind of see we might call this a dozen or 100 times within a test sequence. So what happens if it comes along and it turns out that your 2527 MUX isn't good enough and you need to put in a 2530B matrix? You need something that has more capabilities. Well, a MUX defines a single channel, and a matrix defines a series of rows and columns that need to be connected. So now, every single time, every single call to this function requires you to update this VI, which requires you to update this prototype. So if you kind of follow this down, this chain of dependencies, you change your instrument. That instrument requires you to change your driver that talks to that specific instrument. By changing that driver, you now need to change the wrapper that kind of combines the switch and the DMM together. So you change those, and that requires you to update your your driver prototype in TestStand. And by updating that driver prototype, you're now required to resave your test sequence. So one small change on instrumentation really has this really long-term effect of changing everything down the line to your test sequence. And then depending if you're using a universal style test system, you may have a dozen or 100 sequences that are using that instrumentation. And so now you have to change all of those. And so that really could become weeks of effort just because you needed to extend your switch matrix a little bit. So to take a look at the anatomy of a system that uses hardware and measurement abstraction, you still have that test sequencer up at the very top. But instead of calling specific code modules for a particular piece of instrumentation, you call an action or a step type. And these actions are high level. They're things like signal input or waveform output or power supply out or power output. And these are from the point of view of the unit under test. And so these actions now talk down to a mapping framework. And that mapping framework combines information from a configuration file that says, based off of a signal input type, there are certain parameters associated with a signal input type, and I need to map those down to a particular set of abstracted drivers. So the MAL, measurement abstraction layer, defines those actions, and the HAL, the hardware abstraction layer, defines what a particular type of instrument must do. So for instance, the signal input is going to maybe define some connections and some measurement devices. And so the hardware abstraction layer defines how to make connections, or the syntax for making connections or taking measurements. And then at the bottom level, you have your instruments, and you have some very specific interfaces to those. So there's a set of APIs associated with these, and we'll kind of blank out the individual pieces. An API is really just it's an application programming interface. It's a set of functions and methods and parameters and syntaxes associated with getting information from one piece of code to another. And so your abstraction framework is really defined by a set of APIs. At the lowest level, you have an instrument API. The instrument API is mostly just defined by the instrument vendor. So a NIDMM uses some NIDMM functions in LabVIEW, and those functions are specific to the NIDMM series. You can't use those on an Agilent DMM. Your Xantrex power supply has some certain GPIB commands associated with them. You don't really have control over that. You have to conform to that particular API defined by the vendor. So in order to interface that with an abstraction framework, you define a hardware driver API. And this is what goes one level above and says, if I need to switch, I might need an array of connections. And so that array of connections gets converted by your hardware drivers into the instrument-specific commands in order to connect your switches, but whether it be a GPIB device or an NI switch device. So in order for your high-level system, your test sequencer, to communicate with that hardware driver API, you define a configuration API. And that configuration API is essentially really controlled by however you want to store your data. And so at Bloomy, we have something called the UTS software suite, and as part of that, our abstraction framework is called the hardware access framework. And that configuration API for us is really just an Excel file. And that stores all the information to convert that alias, that measure 5-volt rail that we talked about at the beginning, into the specific commands that go down to those instruments through that hardware driver API. So the final API is the measurement API. This is your measurement abstraction layer. And there's really two sides of it. At the bottom level, you have basically defined the information that gets passed through your mapping framework to your hardware driver APIs. And so in the case of a signal input, the measurement API backend is defining the alias that you want to measure and how you get that measurement back up, that numeric that comes back up to test stand. So in test stand, how many people here have used custom step types in test stand? Cool. So in test stand, that measurement API is your pre or post step. And then the measurement API backend. The measurement API front end is essentially your edit or your configure step. And so that's what you use to configure, or to allow the developer to configure what information that gets passed all the way down so it gets down to that instrument API. So to kind of think of this in a slightly different way, let's use hardware as an example, because it's a lot easier to picture hardware. When you develop a test system, you usually have some sort, or a universal test system, you have some sort of base set of instrumentation. And that base set of instrumentation is very generic. You don't touch it often. You may develop it and not touch it for many years. On the other end, you have your unit under test. And so in order to map from that generic instrumentation to your unit under test, you use a test fixture or an ITA of some sort. Sometimes it might be a cable. And that test fixture takes those generic connections of your base system and maps them to the specific connections of your unit under test. Along the same lines, in software, you have some instrument drivers. You might develop them once, or as you add new instruments, you might need to develop a new driver. But they're very generic. They don't get changed very often. At the other end, you have your test sequence. It's very specific to your unit under test. And so with an abstraction framework, what you can do is you create a configuration file that maps from those specific actions of your unit under test down to the specific commands of your instrumentation. Good. So let's take that same example we did before of the switch DMM and break it out for an abstraction framework. So at the top level, you still want to take your measurement. In this case, though, we're going to call our measurement abstraction layer. And here, we're using our signal input. And so we're going to say, I want to take a signal input, and it's using an alias called 5-volt rail. So we call our signal input type, or this is our step type in test stand. And our signal input is kind of like creating a recipe. It's saying, I need to connect something, I need to take some measurement, and I need to disconnect something, all using this 5-volt rail signal name. So it passes that information down to your mapping framework. The mapping framework aggregates that with your configuration file. And the configuration file has an entry for 5-volt rail, which says I have a connection associated with 5-volt rail and I have some measurement device. That's because this signal is configured as a signal input. And so this is part of that API scheme that I talked about, where you have to define what the inputs and outputs are for each individual type. So that mapping framework takes that information from your configuration file, calls the appropriate drivers, and those appropriate drivers call their particular instruments. So if we need to make a change, that exact same change we talked about before, all we have to do is change this configuration file. So instead of pointing to the 2527, we now point to the 2532B. Instead of having channel 7, we have row 0, column 0, and row 1, column 7. And that information gets passed to the mapping framework, and it calls the appropriate driver for the appropriate instrument. And you'll notice nothing above that mapping framework ever had to change. Your test sequence would never have to change, and any of your test sequences wouldn't have to change. As long as you have a driver that's capable of handling what's defined here, and that's basically part of your hardware abstraction layer, all you have to do is make a change to your configuration file, and it propagates through. So to kind of break this out a little bit more, let's take a look through. We'll kind of walk through each of these and talk about the APIs associated with them. So first, at the highest level, you have your step types, or your actions. And so these are things like signal input or set power or waveform output. In test stand, on this front end of your measurement API, you have a configuration dialog where you might be able to select or type in the alias of the measurement you want to make. In this case, measure 5-volt rail. And so we pass some signal input down to our step type or our action, and we expect a return value to come back. So on the back end, you have a VI that really passes that exact same information. You have a string going in, which is the signal name or the alias. And on the output, you have a numeric value. And so this is under the hood. This is that pre or the post step as part of your custom step type. And so now we're getting a little bit more specific. As we pass along that alias along, now we're saying connect some switch using an alias, measure using an alias and expect a return value, and then disconnect that switch using your alias. So to propagate this down, that information now goes to the mapping framework. The mapping framework starts getting more detailed. It's saying, okay, I need to connect. I need to know what device I'm going to connect, and I need to know what signal or channel I'm going to connect. Same thing, the measurement. I need to know what device I'm measuring with, what channel, and maybe some information about its configuration. And then I need to disconnect the same device. So in your configuration file, in our case it's Excel, it could be a database, it could be a text file, it doesn't really matter. We store some connection information, which is a device and a channel, and some measurement information, which is a device, the channel, and the mode. So the mapping framework takes the detailed information here and starts passing it farther down along to the hardware driver API, or your hardware abstraction layer. And here we're saying connect, and we're passing these now specific information down to that hardware API. So connect, configure, measure, and disconnect. So as we propagate it farther, we pass that information to our switch driver. This is in our hardware abstraction layer. We pass the measurement device and mode and channel to our measurement driver. So we may have a driver for our particular DMM in this case. We then call the measure function from our DMM, and then we call the disconnect from our switch. Each one of these drivers could be a packed project library or a LabVIEW project or a DLL that has all of the functions necessary for it. And then it starts, from them, they pass down the very specific commands for an instrument. This could be the GPIB or the Skippy commands that go down to a boxed instrument. This might be the NI switch and NI DMM driver functions that you use when you would write a specific driver. And so that goes down to finally to the instrument. So what options do you have for implementing your own abstraction framework? Initially, you could just write very specific code modules that do exactly what you want. The benefit being you don't really have to think about anything in the future. You just really implement what you need. However, with very little additional forethought, you can use out-of-the-box abstraction, and this is where we get into the IVI. If you write an IVI driver, or a driver wrapper around IVI, you now have abstracted to many different, say, power supply vendors. So you wrote one driver, took you maybe a little bit extra work, probably not though, and you can now use multiple power supplies or multiple switches. So there's a lot of out-of-the-box abstraction that's readily available from IVI. Skippy is a command protocol, so IVI kind of supersedes Skippy, so if you implement IVI, you're probably all set. NI product family drivers. So NI switch, if you just write a driver around NI switch, you're immediately using out-of-the-box abstraction. The NI switch drivers, if you just use define 2 connections, you can use that for over 100 different devices. Each device has multiple topologies. So right there, you're getting a lot of abstraction built into it. And then NI switch executive. Of these, the only one that's actually, I would call switch executive actually a measurement abstraction layer, because you're defining things from the point of view of the unit under test rather than the instrument specific or the device type specific commands. So there's a lot of out-of-the-box abstraction readily available to you, and TestStand even has plugins or has step types specifically geared around IVI. So you can get a lot of abstraction just right there. Now, if you want,
bring IVI-C, right? Not IVI-com.
Yes. Okay. So now, if you want to integrate this so you have a big, high-level abstraction framework where you can define everything from the point of view of the unit under test and not worry about interfacing with your instruments directly, it's probably going to either require some custom code development or start with an existing framework. And so by integrating into a unified framework, you really get an overall approach that's a lot easier for developers to use. So, and I get a little bit more into the benefits of this later, but it allows you to kind of separate the roles of the architect and the developer. You provide an API that all of your developers can work with. It's very simple to use. And then you can define things, or you can implement your individual application requirements as part of the architecture, or as part of the framework. So like I said, there are existing frameworks available. NI has a measurement utility that uses the Actor framework. And this is basically a starting point for, it's probably better for system architects. It requires some code development, but it allows you to create your own abstraction layers. And at Bloomy, we have what I mentioned before is our hardware access framework. This is more specifically geared as an out-of-the-box solution for TestStand to allow you to define these configuration files and it comes with pre-existing step types and plug-in drivers, so that if you find a driver that doesn't work with it, you can write a new one, drop it into a certain location, and it'll just start working with the program. So there's some existing frameworks. If you want to write your own, we'll talk a little bit about some guidelines for these. So kind of walking through each of these APIs or each of these sections. When you develop a measurement layer, you want to do everything from the point of view of the unit under test. The idea is that your test developer is essentially implementing a test procedure in TestStand so that you want it to essentially look almost identical to the test procedure that's on written paper. TestStand custom step types are really awesome for defining your measurement abstraction layer. It gives you the front end, that dialog that pops up when you hit configure, and it gives you the back end, the pre or the post step that you call that actually implements it, the function at runtime. You're never going to be able to abstract away everything. So really implement the most common functions and if you put it together in a scalable way, if you find something that is lacking in your architecture and you need to add it, you can always add it in the future. But if you try to develop everything you can to abstract away the world, you're basically just going to require your developers to write software again. And so that's not really the idea behind this. In TestStand, when you use those custom step types, you can actually define an insertion palette, and you can separate those into functional groups, analog measurement types and digital measurement types. Maybe you have connection types or power types. You know, if you do a lot of RF, maybe you define a whole section for all about setting up your RF instruments. And so, but by separating those out, it makes it really easy to utilize them for your developers. Really big one. Automatic interface with that configuration file. So with the hardware access framework, what we've done is we've made it, if you can see on the right there, there's the analog input configuration. There's a combo box. And if you configure a set of analog inputs in your configuration file, this combo box will automatically update with whatever is available as an analog input. Same thing goes for power or digital inputs. And so this eliminates developers inputting typos. It makes it so they don't have to have the configuration file side by side. It really allows them to see what they're trying to do, select it, and move on to the next step. And finally, you never want to alienate your power users. So you always want to give some sort of programmatic or advanced access to your step types. In Teststand, this is really easy because the step types, you store all of that information in properties. So that really says if you're using an object-oriented approach, don't just flatten that object to a string because you never really will allow your developers to be able to access any of those programmatic properties. For instance, if you had 100 different analog input measurements for channel 1 through 100, you wouldn't necessarily want to drop down a step type every single time. You want to be able to use the power of Teststand, use loops or subsequences to access these. So what we've done is we've made it so that through pre-expressions, you can define that signal name. So advanced operators or advanced developers always have access to the lower level functions if they need it. Because if it makes it harder for them to do their job, they're not going to use it. So going down to the mapping framework, here's where you're really defining how your aliases, the names of your signals or your power supplies, get mapped to specific hardware. So really what we're talking about in terms of this mapping framework is the format and syntax of your configuration file and how you get that information to map up to your measurement layer and down to your hardware layer. So what we've done, you can define it in many different file types. You can use XML or databases. Like I said, we use Excel, and actually really it's a tab delimited text file. The main reason we chose that is it's really easy for any of the systems we deploy to. Being an integrator, you know, we don't know where these are going all the time. We don't know what's going to be available on the PCs. Everyone has Notepad. You can always open that up and edit it if necessary in Notepad. Separate areas of abstraction. And so one of the things you'll notice here is I have 3 sections set up: instruments, signals, and connections. By separating those major areas of abstractions, you can kind of make a hierarchical level of abstraction. For instance, my 5-volt rail DMM measurement, it references my instrument name DMM, and the instrument name DMM references a driver, which references a physical address in the system. So by doing that, if I have 100 DMM measurements in my system, all of those signals are referencing the instrument name. That's an alias for that instrument. And so by doing that, you're much more able to, if you need to change where the DMM is in the system, maybe you deploy to a different system and it's not called 4065 DMM, it's called device 3. All you have to do is update that device 3 and your test sequence stays the same, there's no changes. Same thing with those connections. Some signals may require some connections associated with them if you have a switched DMM. Other signals don't. If you're using, if you have 24 analog inputs, you may not need to multiplex those. And so doing that same 5-volt rail measurement with our DMM, you'll notice I define a connection, which is DMM to 5-volt rail. That connection is an alias which defines some actual physical connections in the system. The analog input one doesn't define that connection because it doesn't need to be switched. And so you can use these at different levels of abstraction to make it easier to make changes and make it easier to configure your system. And finally, leave room for implementation-specific syntax. If I had defined this file with all of the parameters of the DMM and then all of the parameters of the analog input and then all of the parameters of some scope, I would have 100 different columns in this file. So rather than do that, what we've done is we've identified an instrument config field. And that instrument config field is filled with syntax based off of whatever instrument you define. So if I changed that DMM to a DAC, I would have to change the syntax in there from DC volts, 5.5 digits, 100-volt range, to analog input 0, reference single-ended, and 0 to 10 volts. But once again, I'm still not changing my test sequence. Really, you configure this once, and then you don't have to worry about it. Just like rewiring a fixture. If you rewire the fixture, you don't want your test sequence to change. All you have to do is you modify it in your configuration map that goes between them. And by doing that instrument config, it promotes scalability. If you add a new driver that you haven't thought of or a new device you've never thought of, you can always fill that instrumentation config field with the particular parameters of your specific device. And one of the things that we've done recently is we've actually created a configurator for this so that you don't actually even edit the Excel. If you choose DMM, it will show you the particular parameters for DMM. If you switch DMM to DAC, it'll show you all the DAC particular parameters. If you switch it to a waveform with a scope, it'll show you all of the horizontal and vertical configuration parameters for the scope. So finally, hardware driver guidelines. What you're trying to do is define the inputs and outputs for interfacing with a type of instrument, and then translate those generic instrument type parameters to the specifics of each individual device that you have in your system. As much as possible, make use of out-of-the-box abstract drivers, IVI, Skippy, family drivers. And really importantly, plugins allow you to create new drivers without modifying your base code. So in the hardware access framework, before we implemented a plugin architecture, every time we added a new power supply or a new switch device, we had to modify our code base. We basically had essentially a case structure that selected if the instrument is this, call this driver. If the instrument is that, call that driver. When we went to a plugin approach, now when someone said, hey, I have a new driver, a new power supply, I'm not the one who has to write that driver. I can say, here's a template. This is how you write a driver. Write the driver and put it into a folder. And so now all of the developers can write their own drivers, and the core functionality stays the same. Now that's really nice for me as the architect who's writing this. I don't have to input every person's different device, but it's even more important for a regulated industry where if you change your code, you have to retest. So now every time you add a new driver, technically you need to requalify your entire operation. And so by providing plugin drivers, you're able to add functionality without modifying base code. And just like the measurement abstraction layer, always allow advanced access. With your hardware abstraction, you're not going to be able to abstract away every function. Maybe a particular power supply has a ramp mode that you can define a waveform that it ramps up through. You're not always going to be able to not every power supply can do that. You're not going to necessarily want to abstract that away. But if you allow developers access to that instrument reference, they can now call all of the functions that they need to in order to modify and create their custom functionality. So just like with the measurement abstraction layer, you never want to alienate your power users because if you make it too hard, they're never going to use the system. So in summary, it's a huge initial investment, but typically it will pay off in the long run, especially if you have a long running program, if you have a lot of units that you need to test. Based off of that return on investment calculation, it seems to be about 4 to 6 devices or product tests typically will pay for an abstraction layer. Plan up front, but don't think too far ahead. You're not, if the more you planning is good. It's really good to figure out all of these different APIs, but if you try to abstract everything away, like I said, you're just going to end up you're just going to be writing software again, and that's not the end goal. And what was I going to say? Test and custom step types are really if you're using testing, an awesome way to implement that measurement layer. And when you're using plugin drivers, packed project libraries, there's some people who really love them. There's some people who really hate them. With teststand, they're a huge help for deploying because you have one file that is all compiled code. You don't have to worry about searching. You don't have to worry about your VI library on one machine being on a different machine. All of the dependencies and everything are wrapped up into that PPL. And so when you're deploying plugins, this is really helpful because you can make sure that your plugin is always going to work and always has the dependencies that it requires. And finally, let what you know guide how far you go with this. If you don't feel comfortable implementing an object-oriented approach, but you're really happy with producer-consumer, there's nothing wrong with that because you're going to be the one that's maintaining this in the long run. And so use your abilities to really define how far to take this.